Assalamualaikum warahmatullahi wabarakatuh. Our group will present the topic mass spring damper system for this project. Our group consists of me, Isa Ardini, binti Muhammad Hasri with the metric number 201130, and Nur Darili Batrisha, Nurul Amanina, Nur Dalila, and Nur Fatia Shahira. Firstly, I'm going to start off this presentation with the introduction. To solve this problem, we must first fully understand what mass spring damper system really is. And to do that, we must understand the meaning of mass, spring, and damper. Firstly, mass means the way of storing an energy. In every single object, mass plays a big part in causing the object to have a gravitational weight to keep it static. Mass is a dimensionless quantity representing the amount of matter in an object. And on the other hand, spring means the way of doing work to bring it back to the equilibrium position. It is easily the constrained movement of going upwards and downwards. And lastly, damper means the dissipation of vibrational energy in each cycle. It is a device that constrains, guidance, and represses. Putting all of the meaning of the words together, mass spring damper system is an active system that uses both spring and a damper to go against the outside force. Spring will absorb and release the energy. However, it does not know how to control the rate of the energy that is released. Hence, the damper will do the work of absorbing and releasing the shock impulse, but at a controlled rate. This will ultimately keep the object that the system is in safe. Some examples of this system are car suspensions, car tires, and toys like trampolines and pogo sticks. Our group has two objectives for this project. The first objective is to observe the model that we choose as the second differential equation. And the second objective is to manually and numerically solve the IVP model that we choose using Laplace transform and Python.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Fatia Shahira binti Ahmad Marzuki. My metric number is 2017796, and now I'll be presenting on the mathematical formulation of this model. The model of a mass spring damper system is written as a second-order differential equation with two initial conditions given, usually the mass's initial displacement from some datum, as well as its initial velocity. The basic building blocks consist of masses, springs, and dampers. One common example is the suspension of a car, whereby the car itself is the mass and it is suspended by an elastic spring. A damper, or the shock absorber, prevents oscillation from happening. In this project, the model that we have chosen has an equation of the following. Given the damping constant is C equals to 20, with a mass of m equals to 1, and a spring constant of k equals to 64. The condition of this model is y0 equals to 0 and y prime 0 equals to 0.6. We then have to find the position of the mass at any time t if it starts from the equilibrium position and is given a push to start at an initial velocity of 0.6 meter per second.
Assalamualaikum, my name is Nurul Amanina binti Haidi. My metric number is 2012648. So I will proceed with the manual solution of this problem. Since we are going to be dealing with the second order differential equation, it will be convenient to have the Laplace transform of the first two derivatives, which are Ly prime equal to Sys minus y0 and Ly double prime equal to S square ys minus Sy0 minus y prime 0. And then we apply to this problem Ly double prime plus 20 Ly prime plus 64 Ly equal to 0. Using the Laplace transform, we will get S square ys minus Sy0 minus y0 plus 20 multiplied with Sys minus y0 plus 64 ys equal to 0. And then we will insert the initial condition, which are S square plus 20s plus 64 multiplied with ys plus negative s negative 20 multiplied with y0 and minus y prime 0 equal to 0, and collect all the terms of ys, and we will get ys equal to 0.6 divided by s squared plus 20s plus 64. Then using the partial fraction to solve a and b, we will get a divided by s plus 4 plus b divided by s plus 16. Using the numerator, we will get 0.6 equal to as plus 16a plus bs plus 4b, and we will get a equal to 1 over 20 and b equal to negative 1 over 20. Using the inverse transform, it will give us the solution of the I with p is equal to 0.05 e power of negative 4t minus 0.05 e power of negative 16t.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Dalilah binti Zahari and I will be presenting the computer-aided solution. Firstly, we need to import the necessary SymPy function. For this case, we import the symbol, function, derivative, EQ, dissolve, and also the solve function. Next, we define the values of variables, which is m equal to 1, c equals to 20, and k equals to 64. Next, we define the second order equation and also solve the ordinary differential equation using the dissolve function. Next, we will display the value of constants, which is C1 and C2, which we will get C1 equals to 0.05 and C2 equals to negative 0.05, just like the manual solution. Next, we will substitute the value of constants into the general solution to get the final answer. Next, to plot the graph, we need to import the necessary module, which is sympy.plotting. Lastly, we will plot the graph from range 0 to 1.5 using the plot function.
Hi, Assalamualaikum. My name is Nur Dalilah Batrisha binti Zamri and my metric number is 2018866. So I will continue this presentation with the discussion of the results. The model of mass spring damper system is written as shown in the slides with two initial conditions. And as mentioned before, both of the solutions provided in manual and computer-aided solutions use the case 1, which is overdamping, where c squared minus 4mk is greater than 0, is applied to solve our model. And based on the both solutions, when the spring is immersed in the fluid with damping constant c equal to 20, and it starts from the equilibrium position and is given a push to start it with an initial velocity which is 0.6 meter per second, we have found the position of the mass, and the position of the mass is the yt function written on the slides. From the computer-aided solution section, we have obtained that the graph of the position functions of the mass for the overdamp motion. So notice that c squared is equal to 400 is greater than 4mk, which is 256, where this portrays that it has strong damping force. From the result, this explains that y is approaching to 0 and t is approaching to infinity. Thus, it can be said that the motion decays to 0 as time increases. Next, I will move to the last section of the presentation, which is conclusion and recommendation. In this paper, we have studied the method to find the position of the mass from the mass spring damper system model, and the mathematical model of mass spring system is based on differential equation. Through this project, we found that the mass spring damper system for the overdamping case has no oscillation. It is possible for the mass to pass through the equilibrium position once, but only once. This is because there is a strong damping force, for example, a high viscosity oil or grease, compared with a weak spring and small mass. By using overdamping case in the mass spring damper system model, we have solved the model using two methods, which are manual solutions and computer-aided solutions. After solving the problems, we managed to achieve the same result for the position function by these two different methods. And for the recommendation, in the process of solving the second order differential equation, we must ensure that each step used is valid, reliable, and accurate. To get results that are valid, we need to make sure that we are using the correct model and method to solve our problem. For the reliability of the results, we can improve it by trying to solve the equation repeatedly, and the results are more reliable if we get the same repeated results. And the last aspect that needs to be checked to improve the result is accuracy. Accuracy is how close the results are to the correct value. In order to do so, we must make sure that the results gained by manual calculation are the same as the results from the computer-aided solutions by Python. I think that is all for me. Thank you.